Good day, everybody. I talk today first autoregressive models, which is common for those using time series analysis, but also when we done analysis using longitudinal data, we can model autoregressive in the context of structural equation modeling or multi-level modeling. I present first the basic autoregressive model in the SEM and multi-level modeling context and show you what are the similarities between these two models, and then I continue to show you how to develop the modeling in the context of structural equation modeling or multi-level modeling. I recommend that you read something about these two things. For example, Handbook of Structural Equation Modeling, edited by Rick Hall. It's a very nice book, very large book. And then David McKinn, Introduction to Statistical Mediation Analysis. Then I think you get idea how to model your data. But first, autoregressive model in SEM context. First, I show you how the data should be structured when using structural equation modeling. Then I show you SPSS data, and similar way it has handled in, for example, in M+. There is one row for each individual, and repeated measures are named as variables HEL1, HEL2, HEL3. The number means the time you have measured. And then I use figures and equations to show you what is the simplest autoregressive model. This model is called in the time series analysis as autoregressive model of first order. This first order means that there is dependence only. There is only one arrow between successive measurements. And now I have defined only one beta value. In this process, I think that the process is measured in equal time interval, and therefore I can fix the beta value equal in all time points. The boxes in the figure are observed variables, and when I do that kind of model, you can see that there is two intercepts I must estimate and two variances. One variance is for the first time, and second variance is for other times. I use this example using such kind of value data, which is Nurmi and Taudola collected, and this TAP means task avoidance measure. It's a sum score, and errors. I have reliability only 0.80. The estimate can be seriously biased when using this kind of model. What is important is interpretation of this model. Using this kind of model, you think that the observed value at time t depends only on the previous value of that variable. That means that two individuals who have equal score at time t minus 1 has the equal predicted value at time t, independent of previous value. This interpretation is totally different than, for example, in growth curve analysis. When we constrain the first variance be equal to other time, we suppose that process is stable. It means that the variance is equal in each time. If we have beta coefficient using raw data and it's lower than 1, individual differences at time t are, for example, when beta is 0.707, it's half of the variance at time t minus 1. And residual variance due to changes between successive times. When the beta is equal to 1, individual differences at time t are sum of variances at time t minus 1 and residual variances due to changes between successive measurements. But there also could be that beta is over than 1, and then the process is not, it cannot be stable. Only in the case that beta is lower than 1 or 1, we can talk about stable process. This is an example using MPLUS program. You can see that there is only one beta coefficient, 0.3, and then there is mean value for first time point, variance for first time point, but then there is one estimate for intercepts for time 2, 3, 4, 5, and 6, and one estimate for variance in time 2, 3, 4, 5, 6. Now I have not set the first variance equal to variance in time 2, 3, 4, 5, and 6. And when I do this, the variance is equal between times, but I have when I have made such kind of analysis, I have some problems if I made a constraint. So I recommend that you estimate this first time parameters differently and then try to constrain the model if you think that the process is static. Okay. When I do this structural equation modeling, I get model fits, and now you can see that the model fits is poor. This means that the model cannot explain the associations between observed variables. But one reason in this model could be that the reliability is lower than 1. You have residual or error variances, error variation inside in this variable. One problem is that using fit indices, when you test some process, is that usability of fit index depends on the sample size and model complexity. And one paper you can read related to that usability is Christopher Westland, lower bounds on sample size in structural equation modeling. This is very hard things to decide what is the sample size that you can use these fit indices. But if you have small data, then the estimation process, right? Even you cannot use fit indices. Then I have modification indices, and there are very number of modification indices are high, but there are, I have blue-colored modification indices that you cannot use because I have longitudinal data. We cannot change the arrow from top 1 to top 3, for example. But then there is red-colored modification indices too that you can use to modify model. And this information tells you what is the wrong in your model. Advantage of the autoregressive structural equation model is that we could test the stability hypothesis by using overall fit indices if we have enough data. Further, if the stability hypotheses are not supported, we could re-specify the model with the help of modification indices. That two things are useful when your data is, your sample size is large. But when the model complexity increases, when you put in your model more variables, more arrows, the fit indices need larger sample size to work well. Bentler, in his article, says that 5 times the estimated parameters is enough for sample size, but in the book of Klein tells that 20 times the number of estimated parameters is needed. And this is very high requirements, 20 times the number of estimated parameters. If you have, for example, 10 parameters, then you need 200. But in practice, there could be 50 parameters, 60 parameters, or 10. Then you need a large data. But these comments are related to fit indices. The fit indices works well, then we need large data. Estimation process is you can get estimates, accurate estimates, even with small sample size. One disadvantage is using fit indices that when you modify the model, the fit indices work more as descriptive purposes. And for example, if we use M+, and we constrain some parameters using constraint command, the modification indices are not computed. Okay, then what we can do using multi-level modeling. Autoregressive model using multi-level modeling. The data must be structured in a way that you have one variable, and then I have Hel1, Anx1, Tap1, Math1 variable, meaning that there are 6 time points. There is time variable, which value are 1, 2, 3, 4, 5, 6. And then there is identification variable, meaning that there is one tells that this is the first person you have measured. And then I have ordered, added added variables L2, angst2, tab2, and mat2, meaning that I want to use such autoregressive model in which this L1 is the L1 and L2 are successive measurements. I have moved this value 13 to the time 1, meaning that I want to model this autoregression between successive values. And the last 6th measurement is moved to the 5th measurement. Then I can regress L1 and L2 variables. And the figure tells you that there is within process, within individual process, within person process, and I regress tab 2 on tab 1. And there is black colored circle, fillet circle, which means that the intercepts can vary randomly. But now in this model, I have fixed the variance to 0. So the intercepts has only average value. This random part showing in equation is fixed to 0. When I do this model, the tab 1 is not group-centered, meaning that there is all the values in raw data. But in the model, when I use M+ program, I defined it as within variable. I tell the program that all the variation are within variation. And then estimate the beta coefficient. This model is very similar model than I presented before using structural equation modeling. And when I estimate, you can see that using multi-level modeling, I get very similar results than using structural equation modeling. Estimates are equal, standard error are equal, and also the statistics testing the effect is equal. But when I look the fit index, chi-square tells that this model is not good. And when I go further, I see that model modification index, there is only one value telling that I need to estimate variance for this tab 2. It means that using this multi-level modeling, I need estimate random intercepts that varies between individuals. And therefore, I estimate variance in between level. Usual way to do multi-level modeling is that program automatically estimate the variance for intercepts. And when I do this, I get such kind of results. Now you can see that estimate decrease compared to structural equation modeling or multi-level modeling in which variance is fixed to 0. Now I continue to use multi-level modeling, and now I centered the tab 1, meaning that I use only those variations in type 1 that is related to difference of individual difference between individual means. Now you can see that estimate change totally. It's now minus 0.11. And these three models show you that when you use centering or defined model differently, there is impact in the estimates. All estimates are true, but the interpretation changes. So the advantage of multi-level modeling is that you can separate typical individual level variation and further model the variability in process around the individual level. But there is this disadvantage that the structure between repeated measures cannot test. You can test using SEM, but not using MLM. But what we need is the theoretical knowledge, what we are doing, hypothetical model. Then we can go further using structural equation modeling or multi-level modeling. I now show you some modeling using SEM, how you can continue. The first advantage is in structural equation modeling that when we use latent structure behind the observed variables, we can estimate the error variances. If in my example, task avoidance behavior is some score and its reliability is 0.80, so when I use this kind of modeling, I can estimate those error variance and I get the true variance using latent structure. Now I have fixed the beta coefficient equal, but I have found that I need relax this beta coefficient and I must add one arrow between second and sixth measurement. The model is not stable, there happens something in those time points. But now you can see that the fit indices are good, telling that this model can fit to the data. We can go further in structural equation modeling using, for example, if we think that there is need for latent factor that capture individual level variation, we can add this to this model and test if we need that. In this example, I not need this level factor. You can define the model differently. If you are interested to see exact change score, you can define the model in that way, and I have told that these two models are equivalent. They produce equal fit, and the association between beta 1 and beta 2 is seen in this equation. But when you use this model or difference score model, you can interpret the data in your way. We can enlarge the model using cross-lagged autoregressive models, And we are now interested to see the causality between measurements. In this model, I think I have a hypothesis that task avoidance predicts the math scale in next measurement. There is some relation that when I estimate this, I have fixed all the values in raw data equal, but when I look the standardized values, this first value is related to this arrow, first arrow, and this is related to last arrow. In the standardized, the effect size decrease. We can go further in structural equation modeling, and we can do that kind of mediator analysis. Now I think that anxiety predicts task avoidance, and task avoidance predict math score in later time. You can then test this indirect effect and test the hypothesis of mediator effect. But even we can use sum score, one observed variable. We sum some items and then use only some values. Then we must think, or we can be sure that invariance of factor loadings across measurement holds, at least. That means that you measure the same thing in time 1 and time 2. But I think if you have process data, this invariance holds. When you are interested to mean value, also the invariance of intercept must holds, and you can test also the error variances. What about modeling autoregressive using multi-level modeling? I have now successive scores, math 1 and math 2, and I have used defined tab 1 and math 1 as within variables and get some results. You can see the decrease of this model is 0. I have put all the possible arrows in the model. And in this, you can see that the intraclass correlation is 0. So it means that the variance of math 2 in between level is 0. It's now 0.03 and it's not significant. I can estimate all the variation in within level. But now you can see, because I have defined as within variable, the variation in within level also include level, individual variation in level. Now I have changed the model that I have group mean centered, meaning that all individuals in tab 1 and math 1 is difference score of individuals level, from individuals level. Now you can see that intraclass correlation is 0.20 over than 0.20, and it means that variance in between level is statistically significant. And now the stability coefficient is 0.93. And now task avoidance cannot predict math 2. When I change the model so that I use math 1 and tab 1 as within and between level, I get true estimates, better estimates. the stability is now 0.97 in Witten level, and you can see that the correlation between MAT and Asko models between individual levels is minus 0.60. These three models show you that when you define the multi-level model, it's important to think what variation you want to model and in which level. This is related to interpretation. Which model answered your hypothesis? One advantage is that we can use that kind of model. Now the black fillet circle tells that the regression coefficient is random. It varies between individuals, and now in between level we can regress this random regression coefficient to some observed variables. This means that I use multi-level moderator model. Child's negative emotionality changes this association between father and child between successive days. I can use multi-level mediator model. Then I have random intercept in mediator, and this tells that this variation is modeled in between level. It's a latent variable, and X now explains variation in intercepts, and then there is association between mediator and outcome. But one disadvantage is that if I have measured the data so that the time interval varies between measurements, then I must somehow constrain this beta value. Using structural equation model, I can constrain these beta values so that they are equal in certain time interval. But constraint is not possible in multi-level model. I have not yet idea how to model this in multi-level model. One advantage using structural equation modeling and multi-level modeling is that you can combine those when using M+ program. I think that more of these models can estimate using, for example, SAS program or Stata program. They developed all the time, but M+ has now the feature that you can combine structural equation modeling and multi-level modeling. So I thank you.